Hi, my name is Jacob Arnold. I'm a graduate student here at UC Santa Cruz. And I'm going to talk today about a project that has been going on with some of the collaborators listed here. And the basic goal of this project is to observe and hopefully understand the structure of early type galaxy stellar halos. So for a little bit of background, we know at redshift of 2, early type galaxies are a lot more compact, they're denser. And by the time they get to redshift of 0, they've now grown in size by a factor of several. They now have these more extended stellar halos. It's those stellar halos that I'm interested in. So this is my cartoon picture in the top left corner of how I'm envisioning a Z of 0 early type galaxy. You have your first phase in situ bulge, you form that high redshift of 2 or so. But now it's sitting in this extended halo of stellar material that's been built up over time, mostly by dry mergers of incoming satellites. I think Charlie called it the trash pile on Monday, and I think that's a pretty good description of what's going on. So if you want to actually look at the observed structure of a halo, there's various ways you can go about doing that. You could try to look at the metallicity of the halo. You could look for substructure. Or what I'm going to focus on is the angular momentum. So let me just briefly describe what we already know about angular momentum in early type galaxies. The Sauron and Atlas 3D surveys have really been landmark surveys in this regard. And they've looked at very many galaxies and looked at their kinematic structure inside an effective radius. And one of the main things that has come out of that is that most early type galaxies are so-called fast rotators. So you've probably all seen this plot many times. It's similar to a V over sigma versus ellipticity plot. They replace V over sigma with this lambda parameter. It shows the projected stellar angular momentum inside of effective radius. And over here I'm showing a velocity map for a fairly typical fast rotator and comparing that to a 3-to-1 merger remnant. This has been more the traditional view of how you might form an elliptical galaxy is something like a gas-rich 3-to-1 merger. Gives you velocity structure that looks a lot like what we observe. The problem is I'm really interested in looking at the halos of these galaxies, and when we look at the Sauron or Atlas 3D data, they're just really just showing you what's in the center. And in my cartoon view of early type galaxies, that's telling me what's going on in that first in situ bulge. It's not really telling me what the halo looks like. So really the takeaway message is we need data on larger spatial scales. So the way we're going about doing this is we use DEIMOS. It's a wide field spectrograph on Keck. And nominally we use this multi-slit mask on DEIMOS to target globular clusters. But in the background of each one of those slits, there's enough space for us to also get a little bit of galaxy light through that. So if we use several different masks, we're actually getting random measurements of the stellar velocity field all over the face of the galaxy. And we take fairly long exposures, so we get pretty deep spectra. This is an example of what our data look like. We focus on the near-infrared calcium triplet, and then we take those data and fit line of sight velocity distributions to them, derive the standard Gauss-Hermite parameters, velocity, velocity dispersion, H3 and H4. So this is an example of what our data look like. So I'm showing you that same galaxy as before. I'm showing you the Sauron data there in the center, and on the same spatial scale what the new data look like. So the first thing you notice right away is that idea of this being a fast rotator, this fast rotator galaxy, that idea really only pertains to the central regions. The structure looks a lot different once you look on larger spatial scales. This is just a V over sigma versus radius plot, which shows you that the V over sigma really is falling quite rapidly as you go to larger radius. And I think you agree that when you compare this to a 3-to-1 merger remnant, they no longer look the same on these spatial scales. And I'll just point out that we also have other measurements. I'm just talking about velocity today, but we also have maps of velocity dispersion, H3 and H4, on these large spatial scales. And we're finding a lot of structure. I think there's a lot of data, a lot of information to be mined from these data, and we'll be doing that going forward. So we have measurements like these now for 17 early type galaxies. And this is not a volume limited sample by any means. It's more a representative sample. We have galaxies ranging from small S0s up to bright central ellipticals, filled ellipticals, up to Virgo environment, essentially. So I'm going to show you what some of the velocity maps look like. So just to show you what I'm talking about here, the spatial scales that I'm showing are now 3 effector radii. And for the data that have Sauron or Atlas 3D measurements, I've already put those in this box. And now I'm going to show you what our new data look like. So that's the difference. This is before, this is after. All right, so we're getting a much more global view now of what these galaxies look like on large scales. But we're seeing a variety of things going on. General trends are not necessarily popping out yet. So I want to point an important thing out here. It was one of the first things that was noticed, is that your answers and the way you view elliptical galaxies, at least their kinematics, changes depending on the spatial scale adopted. So over here, this is a V over sigma versus radius plot. The vertical line shows the approximate field of view of Sauron. So each of these galaxies would be called a fast rotator, according to the IFU data in the center. But when you go to larger radius, they all have discrepant behavior. And this changes classic results. This is a V over sigma versus ellipticity plot. I'm showing 2 points which are fast rotator galaxies. They're very similar to each other in this plot. In Sauron data, you go to larger radius, they move quite a bit. But this is a sort of muddy in the waters. We want to try to understand what's going on. So we're going to do a couple simplifications. We're only going to look at galaxies in the sample that are close to edge on, and we're going to try to push to farther radius with our measurements. So the way we do that is to get out to 10 effective radii scales, we now switch over to using discrete velocity tracers, so globular clusters and planetary nebulae. As a part of an ongoing survey called the SLUG survey that will eventually finish 26 galaxies. We'll have these data for all of them. All right, so I want to show you an example of what the difference looks like when you add all these data up together. So this is one example. These 3 velocity maps are all the same galaxy. They're all on the same scale. But I'm just moving from Sauron data to Sauron plus our Deimos data, then adding in the globular cluster data. So in this particular case, we didn't actually gain that much information by going out to the 7 effective radii, but we do see this general trend of that fast rotator galaxy is sitting in a more slowly rotating halo. But this is the more interesting case. This is a galaxy that, with our Deimos data, on 3 effective radii scales, which represents quite a bit of time to just get those measurements, they're very difficult to do, we see rising rotation all the way out to the end of our measurements. And if we stop there, then we would say, okay, this galaxy just continues to rotate no matter how far you go out. But when we include the globular cluster data and go out to 7 effective radii scales, we see it looks very similar actually to the other galaxy. This transition to a slow rotating halo just happened farther out. In fact, this is now 6 of the galaxies in this subsample, and every single one of them show this behavior. You go far enough out into the halo, you realize that there's just a fast rotating component sitting in this slowly rotating halo. And at least in this sample, it actually looks like the rotation of the halo seems pretty well aligned with that central component. So we wanted to figure out what could create this behavior. So we started comparing to simulations people have done trying to create elliptical galaxies. And the first thing we compared to was more canonical idea of, okay, you form elliptical galaxies with major mergers, maybe somewhere between 3 to 1 to 10 to 1. But the problem is binary mergers tend to have rising rotation profiles, while all the data show this decreasing V over sigma versus radius. And that can just be understood when you have a major merger, you bring in a lot of orbital momentum, so you tend to transfer a lot of that outwards. You can have rising rotation profiles. Also, if you're colliding disks together, you have a lot of residual angular momentum in that disk that is not completely washed out in your remnant. So then we compare it to one-to-one mergers, and this is one-to-one, gas-rich one-to-one merger from Lauren Hoffman. This is the same thing just shown on 1, 3, and 7 effective radii scales. And at first glance, this actually looks kind of like what we're seeing in the actual observations. You have the central rotating component, which kind of falls off after effective radius or so. But when you look a little closer at the data, you realize that this actually doesn't quite look like the observations, and there's some problems. We'd have to accept that one-to-one mergers are actually pretty common, and it's somewhat contrived conditions to get this just right. It had to be a low angular momentum orbit. And really, the way we're looking at this now is that these one-to-one mergers like this, they create kinematically decoupled components, and that's what we're seeing here. So there are some notable examples that do look like that. NGC 4365 is one of these galaxies that does have a kinematically decoupled component. Then the rotation, a big kinematic twist, and it actually rotates along the minor axis instead of the major axis. Another example is NGC 5128. This is Sin A. This is a galaxy, when you actually look at it in the sky, it really looks like it had a recent major merger. And it shows big kinematic twist and actually rising rotation out to large radius. So this, when you look closely at it, this is not like the rest of our sample. So then when we finally compared to cosmological simulations, so getting back to this cartoon picture I had of early type galaxies, we believe that the inner in situ bulge was created at high redshift. So we looked at simulations from Avishai and Daniel San Marino, and in this case, they're building that in situ bulge through this violent disk instability fed by cold flows. But then they're allowed to evolve in this cosmological simulation where lots of minor mergers are coming and happening for a long time. So when we observe those simulations just like the data, they start to look kind of familiar. Now these actually look a lot more like the observations. Over here, this is a V over sigma versus radius plot, observations on the left, and then a bunch of these simulations are on the right. They naturally reproduce this falling V over sigma profile very nicely. And since, I won't talk a lot about this, but since I am in the, I did name my talk Chemo-dynamics, so I'll talk a little bit about the chemical structure. There's this classic idea from Searle and Zinn where they surmised that the outer halo of the Milky Way was built up in basically this two-phase assembly process because when you went to far enough radius, you see, this is just metallicity versus radius, you see a very flat metallicity gradient. Essentially, metallicity becomes uncorrelated with distance from the center of the galaxy. And we're just getting to the point now where we can start to observe this in early type galaxies using their globular cluster systems. And we are seeing flat gradients. I would say this is more suggestive than definitive, but it is suggestive of this overall picture. All right, so I'll finish off with my summary where I show observations here in the center and compare that to cosmological simulations and to major merger simulations. And I'll let you be the judge which one you think it looks more like. Thank you.